Welcome to Lecture 21A, entitled Definition of Circulation and Flux and Geometric Interpretation of the Divergence and Curl Operators. So this is basically now a teaching module which involves a couple of new concepts, and we'll be using these concepts throughout the remainder of the course. The material for this lecture comes from Reading Assignment 4, Sections 1.8, 2.2, 2.3, and 2.4. The objectives are to understand the meaning of circulation and flux, and from this we're going to basically define what we call the divergence curl of a vector field. This was for 2D as well as for 3D. The concepts and visualization skills, first of all, are conventions, specifically conventions for tangent vectors and normal vectors. Then the concept of circulation and flux, and then the definition of divergence and how to compute the divergence of a vector field, and also finally the definition of a curl and how to compute the curl of a vector field. As usual, the second slide is just an outline of the slides to follow, so I leave it up to the reader just to go through each one of these particular items in turn, and we'll move on to the next slide. All right, so let's first start with a simple thought experiment. And we're going to stay with a two-dimensional representation of a field because it's somewhat easier to understand in terms of where we want to go using 2D fields because they're easier to graph. And so what I'm essentially stating is that if you take any vector field in 2D, then essentially we can break it up into two types of fields, which are essentially have completely different properties. One of these fields, which appears to be of a source type behavior, we'll talk about that later, and one which has a circulation type behavior. And we're going to start with a very simple field. Always start with linear fields because we can do lots of things with linear field in terms of developing intuition. And so what I'm essentially saying is that we have these two fields. This first field we'll call a flux field. And this is a radial field, xy. We discussed this earlier in one of the preceding lectures. And then we have another field which we're going to call a circulation field, which has this form. And this would mean that the field forms closed loops. And if we take the sum of these two, we're going to essentially say that this is the total field. So we're saying that the total field basically can be represented by the superposition of two fields with totally different properties. One of them which we associate with a source, and another one we associate with rotation. And so we've just added these together to produce this total field here. All right, so next thing we're going to do is we're going to find a contour, and we're just going to keep it simple, a circular contour of radius r. And you'll notice here, for instance, I have graphed the field, which is purely radial. This is F flux. Over here, circulation would be the black arrows that you should see here that form closed loops. And this one is just the sum of the two, which looks more or less like a spiral. Okay, that's the sum of these two fields produces a spiral. The contour is this one that you see in red. And we're going to be, by convention, we're going to be traversing this contour in a counterclockwise direction. And so the unit differential vector tangent to this contour is t bold ds for this, as well as for this. Also, by convention, if we're going around a contour in a counterclockwise direction, then the normal to this contour is to our right, which is what you see here as nsds. So this is basically the unit normal vector, the normal to the contour, this circular contour here. So the first thing we would do is parameterize this contour, and we're going to parameterize with an arbitrary radius r. And so this is the line that we see here, r being the radius, cos t sine t, and t ranges from 0 to 2 pi. So that would mean that this arrow basically makes one full circle as t goes from 0 to 2 pi. So TDS, we know how to do the calculation. This is basically unit tangent vector. You can just take the derivative with respect to t, dt, and this basically gives you TDS. Similarly, if you want the normal vector, which is going to be required, right, then this is perpendicular to this, and we have shown before that this can be represented as r cos t sine t dt, and you can confirm that when you go around the contour in a counterclockwise direction, ns will be always pointing outwards in a radial direction. I mean, that's clear just by looking at this expression and this expression. They're essentially in the same direction, pointing outwards. Anyway, these are things to keep in mind. And so what we're going to do is now we're going to make use of the vector field and the different contours. This is a contour involving a tangent, and we're using the same contour. We're going to be making use of the normal vector component. All right, so we're going to compute the circulation and flux, and the circulation is defined as basically taking a closed contour integral of the dot product between the field, which is the circulation component, and the unit differential tangent vector, and integrating around the closed contour. Well, here is the vector f, again from the previous slide. Here's the vector TDS from the previous slide. We take their dot product and we integrate, and if you go through that process, you'll find you'll get an answer of 2 pi r squared. Now, we want to compute the flux, and the flux is associated with taking a dot product between a vector field and the normal to the contour, integrated around the closed contour. So in this case, F circle basically does not change, but now the second vector changes, and so you can see here, this is r cos t sine t dt. If you do this integration around the closed contour, you get a value of 0. If we now take the flux field, and basically perform the same integrations as we've done here, but in this case take a dot product with the differential tangent vector and integrate around the closed contour. F flux has this form, and the TDS basically would be this form here. This is now the tangent vector. Then we end up with a value of 0. On the other hand, if we do a calculation of the flux, right, using this vector field, this is a flux field form, integrating around, clearly this term here and this term are different, and if you integrate this you'll have 2 pi times r squared, r being the radius of the contour. Also, just to sort of be clear, what are the units? Well, since the units of this integral are we call circulation, and the units of ds are in terms of meters, that means that the units of f will be circulation divided by meters, and similarly circulation in the case of the field f, in the case that we're dealing with a flux integral, the units f would be flux over meter. So one observation we can make from looking at these results is that a field that only has a circulation component, right, which would be this field here, has no flux. So if you look at the flux calculation, we got 0. And a field that only has a flux component, so if we look here, has no circulation. So we end up with a 0 here. So it seems like essentially if we're able to break this up into two separate types of fields performing these two types of contour integrals, they act as a filter. They either tell you that the field is pure circulation or pure flux, or some combination of both, in which case both of these would give you terms. So the intuition tells us this might be very useful. All right. What about if we were now to pick a different location? So compute the circulation flux at an arbitrary position in the xy plane. So all I'm doing is I'm saying that create a little contour, but at some location x0, y0 on the xy plane, and repeat the same procedure. All right, so TDS isn't going to change because once you take the derivative of this with respect to t, the x0 is 0, so we end up with the same value for TDS as well as NDS. And if we do this calculation now, given the fact that we're dealing now with a different circulation, and at this particular location, and do these calculations, we find that we end up still with the same value as before, 2 pi r squared. Similarly for flux, we still end up with 0. If we were to compute the circulation, assuming the field is pure flux form, then we end up with 0. And if we then calculate the flux, assuming the field is pure flux form, we end up with 2 pi r squared. So the general conclusion we can state based on our observations is that the circulation and flux for this particular example, not for all possible cases, these are basically linear fields we're dealing with, it seems like they're not impacted by the location at which a computation is performed. All right, so we look at those results and we say, well, maybe it might be useful to try and normalize these expressions for circulation and flux. And we noticed that basically on the right hand side there was a pi r squared showing up. So that pi r squared basically is nothing more than the area of the enclosed by the contour. So let's try to make the circulation flux integrals independent of the area. So what we're going to do is we're going to divide the circulation by the area. If we do that, we end up with a value of 2. So this suggests to us, by doing this sort of division, we end up with a number which does not depend on the nature of the contour. And that's helpful in terms of how we go about creating a definition. So similarly, if we take the flux and divide by an area, we end up with a value of 2. So the general conclusion that this form of normalization, which is dividing through by an enclosed area, allows us to make circulation flux independent of the contour chosen. And it's this procedure basically which will allow us to come up with these definitions, which we'll be showing shortly. All right, so this is just a sort of a simple example of what we've just discussed. This is an interactive simulation that you can click on, and you can see what happens here. You'll find that the variable slider t would be the movement of the observation point with respect to the origin. So this black dot can be positioned anywhere in the xy plane. The variable slider p is the rotation of position vector with respect to the point of observation. So that's little black arrow here. It's basically just moving around, and the shaded circle area, which is shown in pink, the brightness of color represents the strength of the source basically being, in this case, flux, which is obtained by computing the integral. So if that value becomes larger and larger, then this color will change. If it gets smaller, it will be changing a different way. But in this case, we said that the flux was independent. The flux divided by area, or flux for that matter, were independent of position, where we placed this dot on the xy plane. And therefore, if you move this around, you'll see that this color never changes. And so that's something sort of to tell you that at this location, there appears to be a source, and that source basically is independent, the magnitude of that source is independent of where you position that little circle on the xy plane. All right, we can also do it for the circulation divided by area. In this case, here's the field, the circulation field. And if we were to do the computation of the circulation divided by area, again, idea be here that the variable slider t is the movement of the observation point with respect to the origin, which is this black dot that you see here. The variable slider p is rotation of position vector with respect to the point of observation. So the little black arrow here, which basically sweeps around, makes a full circle. And the red vectors, which are pointing upwards here, represent the strength of the circulation, which is the magnitude or the length of these red vectors that you see here, and the axis of rotation, which is the direction of the vectors. In this problem, the strength is a constant, which means the magnitude of these vectors are independent of where you may position this little circle on the xy plane. So this is again peculiar to the fact that it's a linear field. Now clearly here, as and perform, what you'd like to do is to make the circle smaller and smaller, so that you focus only on the point of interest, which is the observation point. So we were trying to figure out what is the circulation-like behavior right at this point, which means a limiting process would make this circle smaller and smaller. And that's basically how we formalize the definitions for what we'll call the divergence of a vector field and the curl of a vector field, which is basically the subject of the material that's coming up. All right, so this now brings us to the formulation. So let's look at the definition of what we call the divergence of a vector field in 2D. So in 2D, basically, we're saying that we're computing the flux and we're dividing by the area. And this is a flux would be over a closed contour, but we're going to let the area go to 0. And as we've seen before, the units for F are just flux per meter if we're dealing with 2D. And so this diagram basically shows that I've created this closed contour. In this case, I'm making it square. Why? Because it's easier from a computational point of view to work with straight line segments. You don't have to, but it's easier to do it this way. You'll notice here that I basically have put all the normal vectors in because we need just NSDS, and the normal points outwards, and we know that we're going to be traversing a contour in a counterclockwise direction. So all these ones shaded in orange are the normals to the various individual segments. The ones in green represent basically the fields computed at the point on a given segment. So there are 4 different positions that we need to be counted for. And this area is just the area enclosed by this square contour that you see here. All right, so we need to do the integration. It's closed contour integration, which in this case we have 4 discrete segments, so there are 4 individual integrals. We also make use of the fact that f dot nsds is fx dy minus fy dx, and recall that nsds was y dot x dot dt, or also could be written as dy minus dx. And so what we're going to do is to do this computation for them using this diagram that's shown up here, and then dividing through by area. So you'll notice here you have f of x plus dxy minus fx dy. So fx dx would be this one. So this would be the dot product between these two, right? And then we have the dot product between these two. But the dot product here and the dot product here, basically one of them produces a positive value, the other produces a negative value. So there's a positive, there's a negative. And we divide by the differential area, which is dx dy. We also have the top and the bottom, and so this would be f of x y plus dy. The dot product between these two would give you a positive entity, and this would give you a negative. Hence you see the 2 terms here. Divide through by dx dy. Well, dy is a common factor, numerator and denominator, so the base of dy can basically be taken out. And here, dx is a common numerator denominator, so the dx can be factored out. So what are we left with here? Basically, in the limit, as a goes to 0, which in this case will be that the value of dx basically is going to 0. This is nothing more than the partial derivative of f of x with respect to x for this term, and partial fy with respect to y for this term. So this is the final expression that we get. But we can actually play a little trick here. We can essentially say, let's create a vector whose x and y components are the partial derivatives, dx dy, which is nothing more than the gradient operator. And a dot product with the vector field f, this being the x component, y component. If we now basically take this as if it's a dot product, this partial x operates on fx, and this partial y operates on fy, and if you basically take the dot product, you add the 2 together. But if we look at this, then we can use simple symbols to say, well, this is equivalent to the nabla operator, the dot product, and f. So this is what we define as the divergence of a vector field, and it basically comes from this definition that you see here. By the way, the units of the divergence of f will be flux divided by meters squared. Why? Because a partial with respect to x is going to give you an additional meter, so this is flux per meter squared. All right, so let's now look at the 3D case. In the 1D case, a 2D case, it was a contour enclosing an area. In 3D, it's a surface enclosing a volume. And so that's the only difference. You'll notice here this is a surface enclosing a volume. And we let the volume go to 0. In this case, the units of f dot nds will be flux per meter squared. This is still being flux, but this is for the 3D case. Right, and so here what we've done, we've taken again a simple cube because it's easier to do the computations. There are 6 faces to consider when we're dealing with a cube. And so these 6 faces enclose a volume of a cuboid. And so we've got the upper face, the lower face, the right face, the left face, the front, and the back. See, there are 6 different faces, which means when we do the integration over a closed surface, there'll be 6 individual surface integrals to consider. And so this is what I've done, is written it out as 6 individual surface integrals, and you can show that basically, what is the differential surface area for each one of these faces. Like this one basically is pointing in the z-hat direction, whereas the one at the bottom would be pointing in the minus z-hat direction. And so we have all the differential surface area vectors here. All right, so the next step is to essentially just substitute the values. You've got the fields shaded in green, the normals to the surfaces in orange, and yellow just being the enclosed volume. And so you can see here basically you're just grouping terms. So this involves basically keeping y and z constant and only x is varying, x plus dx, and a minus. Why? Because if you take the dot product, for example, if we take this one here, this would be these two are in the same direction, so when you take their dot product, it produces a positive. Whereas if you look at the back side, they're in the opposite direction, so you get a minus. And so this happens for every time we talk about 2 faces, this face and this face. that face and that face, top face and bottom face. So we'll always end up with a minus term showing up in each one of these terms. All right, so now basically we look at this and we notice that we have a common divisor dz here, a common divisor here which is common divisor here which is dy dz, common divisor here which is dx dz, and a common divisor here which is dx dy. So that in this case what we're left with is the difference between these two divided by dx, but that's nothing more than the partial derivative of f with respect to x. This will become the partial derivative with respect to y, and this will be the partial derivative with respect to z. And again, as we did for the 2D case, we can write this out in a more compact form as basically just being the gradient operator for 3 dimensions, dot product with the components of vector field f. And if you write this out in compact form, this is still going to be divergence of f, but its interpretation now is that of a 3D field rather than a 2D field. And in this case, the units of the divergence of flux are going to be flux divided by meters cubed. Right, so that's something to sort of keep in mind. All right, now that we basically defined what a divergence of vector field in 2D and 3D is, we now want to basically look at circulation. So from this we'll get the definition for the curl of a vector field, which is essentially telling you direction and strength of rotation. All right, so a curl in 2D, we basically be looking at a two-dimensional, same contour, but now instead of the normal vector, we're talking about the tangent vector, again taken in a counterclockwise direction. And we're dividing by the area. All right, so in this case, basically, we know basically that for circulation, there's an axis of rotation. And this axis of rotation basically would be sticking out of the page according to the right-hand convention. So if we take our fingers and curl them, right, the axis of rotation would be pointing out of the page. Because the field basically, we're talking about a field that's basically in the same, going to be in the direction of the traversal. Anyway, the units of this will be circulation over meter. This is circulation. This is meters, and therefore F has to be circulation divided by meters. Okay, so if we then just write this contour integral out, we can see there's a dot product between the field and a tangent vector and 4 contributions. In this case, we know that f dot TDS would just be f dx plus fy dy. Again, recall what the definition of TDS is. And so now what we do is we compute these integrals, these 4 integrals, and divide through by the area, which is the area enclosed, and we end up with similar to what we had last time, except with one difference being that this is a t rather than n now. We end up with a contribution of this and this being in the same direction, but on this side and this side they're in the opposite direction. And so one produces a positive contribution, one produces a negative, and for the top and bottom similar. Anyway, we can divide through by dy, it's common here. We can divide through by dx, it's common here. And in this case, what we end up with is the partial of fy with respect to x, which is this, after division, and the partial of fx with respect to y, which is this, after division, with a minus sign. And so this term basically, we're going to call the z component of the curl of a vector field. We'll see why this symbol makes sense when we deal with the actual 3D case. All right, the units in this case will be circulation divided by meters squared. All right, so we say z here because the circulation basically is the axis of rotation, which is out of the page. Now in a 2D case, you know, the z direction doesn't exist, and so we essentially call it a form of imaginary vector representing the axis rotation, which is out of the plane. All right, so now that we have basically defined a curl in 2D, we now want to move towards a 3D formulation. And so what we have to do is to consider the fact that when we're dealing with rotation in 3D, we're talking about rotation on 3 individual principal planes. So the principal planes being XY plane, XZ plane, and the YZ plane. And so we repeat the same type of integration that we did for the 2D case, but we look at the 3 different planes in turn. And so for example here, in the top one here, we have integration on the ZY plane. And so we would have a contour, and again this contour would be traversed in a counterclockwise direction, in other words to comply with the right-hand convention. And you can see here that The tangent vectors are all in orange, the field vectors are in green, and the area enclosed by the contour is A, and that the circulation basically is basically producing a axis of rotation, which in this direction is out of the zy plane, which is in the x hat direction. Okay, so that's basically what's shaded in yellow. So if we were to do this calculation, that is the closed contour integral of the dot product with the field and the tangent vector, and divide by this area, then effectively we would end up with this expression involving the partial with respect to z of y and partial of fy with respect to z with a minus sign. It's similar to what we've seen for the case when we did the 2D calculations. So this would be, for instance, in the zy plane. If we're dealing with the zx plane, again, we're dealing with a contour traversal in the counterclockwise direction from z to x, whereas here it was from y to z. And here it's basically going to be from x to y, again, counterclockwise. Always has to be according to the convention. The example here is shown for the case of ax, which is one in the top left-hand corner. And so there are 4 integrals that have to be formed in order to compute a closed contour integral. Again, this is similar to what we did in the previous slide for the 2D case. And so we can just write this out in full. And then after some simplification, we end up with the expression that you see here, which essentially is what I've shown up here. All right, so what we want to do is to do the computation for this one, for this one, and for this one, which is shown here, and put it together, which is basically the next slide. All right, so here was the x contribution that was pointing in the x hat direction. This is for the yz plane, this was for the xz plane, and this is for the xy plane. So what we can do is we can write this in determinant form in this form. So we could say that the x hat component could be written in this form, y hat component can be written in this form, and z hat in this form. And so I'm going to call this the x hat component of the curl of a vector field. Why the cross product? Because this is typically how we express things in cross product form. So this would be the x component of the curl, this is the y component of the curl, and z component of curl. But I can add these all together, right? And it's just basically add them all together, and I end up with this final form, which is by definition going to be the curl of the vector field f. So first row being the unit vectors in Cartesian coordinates. Second row would be the first vector, which was just the gradient vector, and the third row would be the field vector, the x, y, and z component. And if you want to show this in diagrammatic form, just look on the right hand side. Here are your 3 principal planes. Here basically it shows the contour traversals for the individual planes. Each one of them makes a contribution, and the total value, which is the sum of all 3, is this vector that you see here. So that represents what appears to be the apparent rotation of the field at that location, taking count the x, y, and z component. And so that's the curl of f. All right, so just a brief summary of some of the things we alluded to earlier regarding in 2D, that the axis rotation was out of the page. Of course, in 2D, the z-axis does not exist, and so we have to define it as an imaginary axis, and so we use that, define that as a pseudo-vector j. Similarly, for the situation when we're dealing with real numbers, where we could not basically define what was meant by the square root of -1, so we just gave it a label and called it j and called it an imaginary number. Now, we basically know that the imaginary number is a scalar, and we know the real number is a scalar, but if we wanted to basically depict both of them, then effectively in 1D, which would be a real number, would be along the x-axis, we can essentially use the y-axis to describe the imaginary component when we're trying to basically plot values for in the complex plane. And so effectively we can then recycle the notion of a vector, and so we talk about a complex vector rather than a real vector. So these examples here just show you different ways and things that can be written. For instance, a pseudo-vector could be written as a scalar multiple times j, this being a pseudo-vector. Or you could essentially say a is a real vector and multiply by j, with j being basically an imaginary number. This also can be considered as a pseudo-vector. And this is just some geometric properties. What exists? Points exist in 1D, 2D, and 3D. Lines exist in 2D and 3D. And oriented planes exist in 3D space. And to summarize, I've just put the properties of the pseudoscalars in one column, the properties of pseudovectors on the other column. And in fact, the reason I've put this here is because if you look from a historical point of view, how did vector calculus start? It dates back to the late 1800s, and there were two competing approaches. One which was based on the Gibbs formulation, which was intuitively simple to understand. And then there was another one which was based on concepts of algebra and geometry and putting them together. It was at that time too complicated for many people to understand. And yet, in hindsight, it's much easier from an intuitive perspective to understand vector calculus in more than 3 dimensions if one goes the route of geometric algebra. Whereas it becomes much more difficult to take the Gibbs formulation and extend it to higher dimensions. So today in computer science, when we're dealing graphics, geometric algebra is the approach that most people are taking. All right, so that concludes Lecture 21A. Thank you for listening.